بسم الله الرحمن الرحيم. أبناء طلاب الفرقة الرابعة عام شعبة ماثيماتكس، برنامج الخاص باللغة الإنجليزية. كل عام وأنتم بخير. نواصل اليوم محاضراتنا لمقرر Applied 12 The Theory of Special Theory of Relativity. عنوان محاضرة اليوم Chapter 4 Part B Relativistic Dynamics. Section 7 Correspondence Principle. We have found that Lorentz transformation devolves into the Galileo transformation when the velocity of light approaches or tends to infinity, or if the velocity of a particle, of a moving particle, v is much less than c, the velocity of light. V, velocity of a particle, v is much less than c. We must take this characteristics into consideration, and this means that the laws of relativity that we are looking for must refer to their counterparts in classical physics, and this is called the correspondence principle. Section 8 Momentum for vector. The momentum for vector pi is defined as pi equals b and ib4, where b the triple momentum vector and b4 is the fourth component of pi. Now we consider the two frames S and S dash. If pi dash is the momentum or vector measured with respect to S dash, then pi dash is given by this form. To find the relationship between pi and pi dash, we use the Lorentz transformation in this form. B1 equals beta b dash 1 plus v I by c b dash 4, and b4 equals beta b dash 4 plus v I by c b dash 1, and beta equals 1 divided by square root of 1 minus v square I by c square, where v is the velocity of from S dash with respect to S in OX direction, where v is the velocity of this frame of S dash frame with respect to S in OX direction. Now we assume that S dash is the rest frame of the particle, and this means that or i.e. S dash moves with the particle at the same velocity, and in this case the transformation 35, this transformation becomes, when we consider S dash as the rest frame with respect to the velocity, if we consider S dash the rest frame, then B dash 1 equals 0, B dash 1 here equals 0, and the transformation 35 become in this form: B1 equals beta V على C B dash 4 و B4, and B4 equals beta B dash 4 B dash 4, and to find B dash 4 in these two relations, to find B dash 4 we use the principle of correspondence. The principle of correspondence means that equation 36 in the case of classical mechanics, this relation in classical mechanics must be as B1 equals mv, and the other side of 36 can be written as mv equals v divided by c b dash 4, and the beta in the classical case must be written as 1 plus neglected terms. Very small terms can be neglected with respect to 1. And from this relation, it is clear that B dash 4 must be MC, i.e. B dash 4 equals MC, where M is the mass of the particle measured with respect to the rest frame, S dash, and it can be symbolized by the symbol M naught. M here is M naught, where M naught is the rest mass of the particle. And then relation 36 and 37, these two relations can be written or rewritten as B1 equals beta M naught V, and B4 equals beta M naught C. Equation 36, we substitute B dash 4 in C, and B4 equals beta B1 B dash 4. Then 36 relation 36 and 37 become in these two forms: B1 equals beta M naught V, and B4 equals beta M naught C. The general form of this equation, of this relation of being, can be written in the vector form B equals beta m naught V. This relation can be written in the vector form B equals beta m naught V. From this it follows that the momentum for vector takes the form by equals beta m naught V and I beta m naught C. Comparing this for the velocity for vector kappa, we find that by can be written as by equals m naught kappa. Kappa is the velocity for vector, or in terms of components, the momentum for vector by can be written as by mu equals m naught kappa mu, and mu equals 1, 2, 3, and 4. The square of momentum for vector by can be written as by square equals the inner product by and by equals beta square m naught square sin c square equals minus m naught square c square, and this quantity is an invariant quantity under the Lorentz transformation. Section 9, the moving mass. The formula 42 B equals beta m naught V. This formula can be rewritten as B equals beta m naught V, or B equals mV, where m equals beta m naught, or m naught divided by square root of 1 minus V square by C square. From this formula we get if V equals 0 in 48, or when V equals 0, then m equals m naught. When V equals 0, m equals m naught. M naught in this case is the rest mass. According to this formula, it is clear that m varies with respect to V, or m is called a moving particle mass. M in this form is called a moving particle mass, and it is clear that this mass this mass is not an absolute concept, is not constant, is not absolute concept as in the classical physics. Using formula 47, the momentum for vector becomes y equals mv and imc, or b and imc. This is the momentum for vector Section 10, Relativistic equations of motions. Relativistic equations of motion. Assuming that gamma mu are the components of the force for vector, then the correct generalization of Newton's second law is as follows: d by d2 by mu equals gamma mu, and mu equals 1, 2, 3, and 4, where d2 is the period of proper time 2. This is the general form of Newton's second law in relativistic mechanics. The vector gamma is called the Minkowski force for vector, and gamma equals G and IG4. G is a triple vector, and G4 is the force component of gamma. Using the definition of acceleration for vector, the left hand side of this equation of motion, the left hand side of this equation of motion, d by d2 by mu, can be written as d by d2 by mu equals m naught kappa mu, d by d2 kappa mu equals alpha mu, the acceleration for vector alpha mu. And then we can write equation of motion 50. This equation can be written as m naught alpha mu equals gamma mu. Equation 50, equation of motion 50, can be rewritten in detail as equation 50 in detail can be rewritten as beta d by dt beta m naught v equals g, and beta d by dt beta m naught c equals d4. Equation 50, equation of motion, substituting the component of this vector and the component of this vector, Kubinsky force dy d4. Then equation 50 in details takes the form beta d by dt beta m naught v equals g, and beta d by dt beta m naught c equals d4. And if we divide the both sides by beta and we divide here by beta, then d by dt beta m naught v equals g divided by beta, and here d by dt beta m naught c equals g4 divided by beta, and we let beta m naught equals m, the moving mass. Then equations 54 and 55 can be written as, if we put f equals e divided by beta or b d4 divided by beta, then equations 54 and 55 can be or become in the form d by dt mv equals f, and d by dt mc equals b. Equations 59 and 60, these equations are the Newton's second law in relativistic mechanics. Equations 59 and 60 represents the Newton's second law in relativistic mechanics. شكرا لحسن الاستماع، والسلام عليكم ورحمة الله وبركاته.